All right, folks, we're back. This is section 5-2. This is recording number 2. And where we left off, we were just going to start talking about this example 5-5. So example 5.5 through 5.8 are being used to illustrate this formula right here. Now, if you don't mind, before I begin, I'd like to just give you a little bit of generic advice here, and that's the following. It's been my experience, and this is based on teaching, and it's based on being a student for many, many years. The first time you read something like this, it makes no sense whatsoever. It's just impossible to understand what the heck they're talking about. So that's why examples are so important. But what you've got to do is when you look at the example, you've got to go back to the definition and make that connection so that you see the example is following the formula exactly, and that will make the definition more clear. And then as time goes on, it makes it a lot easier for you to read definitions and understand them. So please take my advice on that and follow this procedure. Okay, so example 5-5, we're rolling a die. Find the mean of the number of spots that appear when a die is tossed. So the experiment is tossing one single die. The outcome is you see a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so that's the outcome that you're looking for. The random variable is a 1 or a 2 or a 3, and as you can see from our definition from before, this is an attribute or a characteristic in the sense that that's what's showing up, and the outcome is a matter of chance because you throw the dice. It's a matter of chance what number comes up. Therefore, we call this a random variable. So with these outcomes, 1, 2, 3, 4, 5, 6, there's a probability of getting each one of them. So there is a probability that's associated with each of the outcomes. Well, that's exactly what we mean by a probability distribution. A probability distribution is information or a table, however you want to say it. It can be a table or it can be a graph that associates a probability with a particular outcome. All right, so our formula here, look up here, here's our formula. The mean of a random variable with a discrete probability distribution is, see how it is? It's x1 times the probability of x1, x2 times the probability of x2. Well, that's exactly what we have right here. 1, that's my x sub 1 times the probability of getting a 1, that's 1/6. 2, that's my x sub 2, that's the second possibility, times the probability of getting that particular value. So we're following the formula exactly. You multiply everything out and you get 3.5 or 3.5. Okay, so what is this saying? What does this really mean? When you toss a dice, a die, I should say, when a die is tossed many times, the theoretical mean will be 3.5. Now, notice that even though the die cannot show a 3.5, the theoretical average is 3.5. You should not be concerned or worried about the fact that the mean is a number that cannot really occur. So perhaps you've heard this expression before. They'll say the average family has 2.3 kids or something of that sort. Well, you can't have 2.3 kids, but that's the concept. That's the mean. That's the average number of kids. As he says here, the reason why this formula gives the theoretical mean is that in the long run, each of these outcomes would occur 1/6 of the time, etc., etc. Okay, so I'll let you read that. Now, the distinction here is this is a theoretical mean because we're not really doing the experiment. We're not really throwing the die. I can tell you, this is a very common fallacy in Las Vegas. People that are gambling is they think that the die have some sort of a memory, that they will distribute themselves according to this distribution. Well, that's not true. you could throw a die and you could get a 4 and a 4 and a 4 and a 4. That could happen. So that's why if you had a small sample set, if you only threw the die 4 times or 5 times or something like that, you could get these anomalous results and it wouldn't look like this. Well, that's okay. That's just the way life is. When you have a small sample set, you can have misleading results. This is a theoretical mean in the sense that we're sort of pretending that we're doing it an infinite number of times. Okay, so let's take a look at another example here. The children in a family. Okay, 4 kids, find the mean number of children who will be girls. So here's our sample space. With 4 kids, these are all the possibilities of what you could have. A boy, 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 boy. Here's another one. You could have a girl first, then a boy, then a girl, then a boy, and so forth. Okay, so you have all these possibilities. Now there's 16 outcomes. Now we don't have to write these down to come up with how there's 16 outcomes. There's 4 slots, so to speak, 4 occurrences. So it's in each one of those slots, there's 2 possibilities. So it's 2 times 2 times 2 times 2, which is 16. As far as coming up with what the probabilities are concerned, we unfortunately right at this moment in time we do have to write down all the possibilities because we don't know how to do what's called the binomial distribution yet. We're going to learn that in a little bit. Okay, so we're writing down all of these possibilities. So what are the number of ways, or excuse me, what's the probability of getting 0 girls, 1 girl, and so forth? So again, just like before, the random variable is going to be the number of girls. So whereas before we had an outcome of a 1, a 2, a 3, now we have an outcome of how many successes do we have? How many girls do we have? That's our success, is having a girl. Okay, so we can have 0 successes. That would be an example right here. Boy, 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 boy. We could have 1 girl. Okay, that would be one success, 1 girl. Okay, so how many ways can we do that? Well, here's one right here. Here's one right here. Here's one right here. Here's one right here. And that's the end of it, right? From now on, there's more than 1 girl. So there's 4 possible successes. There's 4 ways of getting 1 girl, and so forth. So you can see how this works, right? So as an exercise for yourself, make sure you understand how we come up with these probabilities. So again, at the risk of beating a dead horse here, this is a probability distribution because we are assigning a probability to each of these outcomes. The outcome of 0, outcome of 1, outcome of 2, outcome of 3, outcome of 4. And each of those have a corresponding probability. Okay, so using our formula in the blue box here to find the mu, and by the way, we're using mu instead of x bar because mu is the mean of the entire population. It's not a mean of a sample. So we come back here, we use our formula. It's going to be, the first guy, the x sub 1 is 0 times 1/16. 1 times 4/16. 2 times 6/16. And if you look back up there to that blue box, you'll see that's exactly what the formula is. You multiply all this out and you simplify it, you come up with 2. So what's the mean of the number of females is 2. So that's how we come up with a mean of 2 for the females. Now, just as a way to kind of put it all together, perhaps, this is an example here of what we're going to see here in a little bit called expectation. I want to mention this to you. You have 4 children, right? The probability of getting a girl is 1/2. So the expectation, if you knew nothing else, if I said, well, my friend has 4 kids, what do you expect the number of girls to be? You would say, well, half of them are going to be girls because half of the time you come up with a girl. So 1/2 times 4, that's the expected value. So that kind of helps you understand his business up here of why was it that he said on average you could expect the number of heads to be 1. Okay, 1/2 times 2 tosses. 1/2 times 2 tosses gives you 1 head. Okay, finally, I'm kind of beating these. I'm talking about all of these because I really want to stress this. Understanding what a probability distribution, the fundamental concept, is very, very important. Okay, so you toss 3 coins. What's the mean of the number of heads that can occur? Well, we had a table preceding example 5.1. I'll let you look at that. But out of the 3 heads, you could get, I'm sorry, out of the 3 tosses, you toss it 3 times. What are the possible outcomes that you can get? You can get 0 heads, 1 head, 2 heads, or 3 heads. Okay, what's the probability of each of those? You look at the table preceding example 5.1, and you'll see you count them all up, and you come up with this. Again, it's just doing the arithmetic, and then we say one more time, this value 1.5 cannot really occur, but it is the theoretical average. Okay, all right. Remember before we had these battery packages? I think I actually talked about this example. Same concept, same song, second verse. It's going to be a certain outcome of you sell the 2-pack, the 4-pack, the 6-pack, or the 8-pack. What's the probability of those things? Well, here's the probability that's associated with each one of those outcomes. So the mean number of batteries sold is 4.56. Okay. All right, so that's all I know about the mean. This is how you figure out the mean of the theoretical mean for a discrete probability distribution. So when we get to the continuous probability distribution, it's going to be a little bit different. But as you can see, it's not as hard as it looks. Once you do a couple of examples, that formula should not intimidate you. All right, so let's make that the end of recording number 2, and we'll pick it up here at the variance and standard deviation on the next recording.